Okay, so we can start.
Okay, great.
Welcome back to the welcome back to this session. The next speaker is Ekaterina KOVACHEVA from Karlsruhe Institute of Technology, and she's going to speak about an In-Silico study on hypertrophic cardiomyopathy, causes of altered myocardial velocities.
Thank you for the introduction. My name is Ekaterina KOVACHEVA. Today I'm going to present you the In-Silico results of a study that I did. And so let's start with the definition of hypertrophic cardiomyopathy. So hypertrophic cardiomyopathy is the most common genetic cardiovascular disease and represents the main cause of sudden death in young patients. So in this presentation, we're going to talk about the symmetric or the concentric phenotype, but there are also other different types. This type is characterized by a hypertrophy of the left ventricular wall. For example, you can see in the picture on the right, in the diastolic state, the wall is thickened, and the systolic even more, obviously. So in the literature, we could find values that say that the wall is about 21 millimeter thick in the diastole compared to the healthy case, which has about 11 millimeter of thickness. Also in this picture, you can see that the volume of the left cavity is reduced. Also in the literature, we could find that the group of Villemain et al. Measured the passive stiffness by using shear wave imaging technique, which is an ultrasound-based imaging technique. And they could discover that the median of the passive stiffness in a HCM group was about 4.6 times higher than the stiffness in a healthy group. So if you look at the microstructure of the tissue, the group around Hoskis and et al. Found that the force produced by HCM cells is reduced by about 40% compared to healthy cells. Also, Aguirre and al. Measured the cell orientations by diffusion tensor MRI, as here visualized in the picture, and discovered that the cells in the HCM case are disorganized and the extracellular volume is expanded. Also in the literature, we could find that the velocities of the myocardium are significantly reduced in the diastole, and the velocities in the systole are also reduced. This was shown by the group around Lee et al. So today we are going to answer two questions. The first one is, how does the thickening of the wall, the stiffening, and the reduction of active force in the tissue alter the myocardial velocity? And the second is, if we assume an altered myocardial velocity is provided, for example, from an MRI study, can we identify the cause of its alternation? And we would like to answer this question by running numerical simulation. So let me first present you the simulation framework. So we use cardiomechanics, which is developed here at the IBT. It solves the linear momentum equation as described in the book of Belichko, and the spatial discretization is done by the finite element method. And here we applied linear tetrahedral and surface elements. In our geometry, we had about 41,000 cells and 7.5 thousand points. For the time integration, we used the Newmark beta scheme. And here in the middle of the slide, you can see the equation. So we have the mass matrix times the acceleration plus the internal nodal forces minus the external nodal forces plus the term of the Rayleigh damping. After we solve this equation, we obtain the displacement in each time step. So down here, you can see two equations that delivers the velocity in each time step after we have calculated the displacement. So in this presentation, when we talk about velocity, it will be this velocity in each time step that we found for every node of the geometrical model. So for our simulation, we used a 4-chamber model of the whole heart, as visualized here. In the ventricle, we defined the fibers by the rule-based algorithm of Bayer et al. And the angles of Streeter were applied. So in the endocardium, we set 60 degrees, and the epicardium, we set -60 degrees. To model the passive properties of the myocardium, we used the constitutive model of Guccione, which models a transverse isotropic material. And here we added an incompressible term. In the table here, you can see the parameters that we used for these models. And those were obtained by a comparison with the Klotz curve, which delivers relation between the volume and the pressure in the left ventricle. The active tension was defined by a curve, which delivers tension over time. And this was scaled by a tension max factor, which was said to be 80 kilopascal. So these values are the healthy values in our simulations. For the boundary condition, we fixated the great vessels as shown by the red color on the picture here. And also we defined a contact pericardium as described in the work of Fritz et al. Here, the contact pericardium ensures that there is a constant contact between the epicardial surface of the heart and the inside surface of the pericardium. Here you can see a video of the contraction of the healthy case of the left ventricle. And down on left, I have visualized the velocity magnitude over time. So you can see in the green area the systole and the peak velocity, and in the yellow area the diastole. On the left of the green area, you can see the atrial kick, and before the atrial kick is where our simulation starts. By the darker line in the middle, the mean velocity is visualized, and also you can see the color code on the left with the about same numbers as here in the scale in the epsilon axis. So this is our healthy case, and we defined variations based on this case. So we varied 3 things. First of all, we increased the wall thickness from 12 millimeter, which is the healthy case, to 18 millimeter and 20 millimeter, which is the HCM1 and HCM2 cases. For both cases, we added tissue to the inside of the wall on the endocardial surface to ensure that the volume of the left cavity is decreased. Also, we increased the stiffness by the factor 4.6 mentioned before, from 162 Pascal to 755 Pascal. And also we decreased the active tension by 40%, from 80 kilopascal to 48 kilopascal, sorry. And so here are the first results. So now we want to investigate how the wall thickness influences the myocardial velocity. On the very left, you can see the healthy case. In the middle, the HCM1 with wall thickness 18 millimeter, and on the right, the HCM2 with wall thickness 20 millimeter at the diastolic state. And if we look at the velocities, we can see that both HCM cases have increased systolic average maximal velocity, and the velocities in the diastole are quite comparable. Also, if we compare the velocities between the HCM1 and HCM2 case, we can see that they are quite similar. So here we can conclude that hypertrophied walls lead to an increase in the systolic velocities and have minor influence on the diastolic velocities. So further on, we increase the stiffness. On the left, we have the healthy case with stiffness 162 Pascal, and on the right, the stiffness is increased to 755 Pascal. And here we can observe that the systolic velocities in the stiffer tissue are decreased, and the diastolic are quite similar. also the same tendency was observed for the healthy case, which is where the wall is 12 millimeter thick. And so we can conclude that stiff tissue leads to a decrease of the systolic velocities and have minor influence on the diastolic velocities. And further on, we reduce the tension. So on the left, you can see a simulation where the tension max is 80 kilopascal, and on the right, it is decreased to 48. Here we can see that the velocities in the whole cardiac cycle are decreased, and also the same results we obtained for the healthy case. So we can conclude that reduced active tension in the tissue leads to a decrease of the velocities in the whole cycle. In the next comparison, in the one HCM simulation, we increased the stiffness, and in the second, we decreased the tension. And here we could see that the velocities in the systole are comparable, and the velocity in the diastole differ. And here we can conclude that either stiffer tissue or reduced active tension leads to similar velocities in the systole, which are both lower than the healthy case, but result in different diastolic velocities. And finally, we have the comparison between the healthy case and the HCM case with stiffened tissue and reduced tension max, reduced active force. And here we can see that the decrease during the decrease of the maximal average velocity during the systole is significantly, and during the diastole, it's just slower. So now here we can conclude that a combination of stiffer tissue and reduced active tension lead to a significant decrease of the velocities in the systole and a decrease of the velocity in the diastole. So let's remember our second question. If we assume the outer myocardial velocity is provided, can we identify the cause of its alternation? And after seeing the results, we can conclude that lower velocities in the whole cycle are caused by reduced active tension. And if the velocities in the systole are significantly reduced, then this reveals additionally higher stiffness of the tissue. If the velocities are only lower in the systole, then this is caused by higher stiffness of the tissue, but healthy active tension development. And if higher velocities in the systole are observed, then this is caused by the hypertrophic left ventricular wall, but with healthy stiffness and healthy active tension development. Now let's remember what we found in the literature. So Lee et al. Showed that peaks in the systolic phase are reduced. This we could actually also observe. They also showed or measured that the velocities in the diastole are significantly reduced. And we could see that they're reduced, but not really significantly. So that's why we set an orange OK here. And yeah, in the future, we would like to further investigate the effect of a circulatory model. We would like to add disorganized cells orientation as shown in the work of Riga et al. And also would like to calculate the long axis velocity in order to directly be able to compare the values that we found in the literature. And to finalize, I brought you a video where on the top we show the motion pattern, or yeah, the motion of a hypertrophic heart, which we took from the Cardiac Atlas project, and it was part of the Sunnybrook cardiac data set. And on the bottom, you can see the cut through the short axis slice, as here visualized in this picture from our simulated contraction. And we could observe that the motion is similar, but it's not identical, since these are two different hearts and from two different patients. So thank you very much for your attention, and I'm open for questions.
Thank you, Ekaterina, for the interesting talk. I would ask all the audience if they have any question to raise a hand or drop a question in the chat.
Okay, thank you.
So we have some time for questions indeed now. Well, I have a question, if there aren't any from the audience, which is about. Okay, did you check? Did you study if there is any difference on your results, whether the hypertrophy is, let's say, distributed somehow homogeneously in the myocardium, or if there are some particular regions in which the hypertrophy is stronger?
No, actually, I only observed the symmetrical or the concentric case where the hypertrophy is distributed quite similar. And yeah, I haven't observed a case where we have, for example, the septal hypertrophy or the apical hypertrophy.
I see. Okay, thank you. There is another question from Nicholas Barnafi, who asks, he's wondering if these results hold for finer mesh, as they look rather coarse. And also, he would like a comment on the generation of fibers for the full heart, for the whole heart.
Yeah, so for the fine, we haven't tried to simulate fine meshes. So for now, our framework allows for now to simulate only such coarse meshes, and that's why I cannot try out to simulate more finer mesh. And yes, the second question was about the fibers. Yeah, so I used the algorithm of Bayer et al. From year 2012, and for both healthy and hypertrophed case, I defined this same boundary condition, which is 60 and minus 60 degree on the APN endocardium. But as I mentioned at the beginning, there are findings that the fiber are distorted for the hypertrophic case, and this is part of the future work, and needs to be explored further on. What is the effect of these changed fibers?
Okay, thank you. Is there any last-minute question? Okay, if not, we thank again Ekaterina for her presentation. And
I think, sorry, Ivan, there is another question by David.
Okay.
In the chat.
Thank you. I didn't see it. Okay. So if Ekaterina is still available, David would like to ask if you have introduced the active force in the constitutive equations.
Okay, so the for us in our definition, we have the active stress approach, which is addition of active force plus passive force. So the active force is separated from the constitutive equation, and it is defined as force per time. So for now, I define a curve or predefine a curve that delivers me the force per time. And I can scale this curve by a factor. And this is how I applied it, the reduced active force.
Okay, thank you.